Exactly. Okay. So I'm going to talk about something rather different. This is a software tool for use in analyzing images of galaxies. It's a new code for doing what's called galaxy decomposition. There are basically two parts to the talk. One is talking about the code itself, and the other is a little bit at the end talking about fitting low signal-to-noise images of galaxies and biases that can result when you do this sort of fitting, depending on the statistical approach you take. Okay, so what's the basic idea we're talking? We're talking about having images of galaxies and trying to model them. We model them by decomposing them into the sum of one or more 2D surface brightness functions. So a simple example would be a bulge disk decomposition, where you model the disk as an elliptical shape with an exponential profile, the bulge with another elliptical shape, maybe a different shape, with a Core-Sersic surface brightness profile. This is particularly useful if your galaxy has non-axisymmetric structures like bars, for instance, or some rings, or if you're trying to disentangle one or more overlapping sources, say a neighboring galaxy that's interfering with your galaxy. This does assume that the galaxies can be modeled as the sum of additive components. It's kind of a caveat that should always be borne in mind. Okay, there are, of course, codes which do this already. The three most popular that you're likely to have heard of are GIM2D, which is the oldest. It's designed to run within IRAF. Buddha, which is a separate Fortran-based program, has more functions available. And Galfit, which is possibly the most popular one. That's based in C. The most versatile of these, also the fastest. There are other codes, of course, that individual groups have. These are the ones that you can sort of find on the web. Now, I think there are still some drawbacks and limitations, otherwise I wouldn't have gone to the trouble of making my own code. None of these are open source. In most cases, the source code is not freely available, or you can get it, but it's a little bit awkward. And this means that you can't play with it to add in any improvements that you think you might need for your purposes. Plus, there's some limitations on platforms. For instance, GIM2D only works within IRAF. It's a personal taste issue. I think the interfaces are a little bit awkward. Maybe more significant from my point of view is that they have a limited number of available functions. So, for instance, the simplest case, it's just an exponential and a disk, and those are your only choices. The others have more functions, but you're still sort of limited to what's baked into the program. You may have some idea that, okay, in this particular galaxy or this set of galaxies, we think the function of this structure should be X, and you don't really have the freedom to explore that. So, Imfit is yet another 2D image fitting program. It's built to be modular, object-oriented design, written in C++. Uses open source code for things like image input and output, for fast Fourier transform convolution, and for all the minimization algorithms. There's a special focus on making it easy to write and add new image functions, that is, new surface brightness 2D functions. It's also written to be relatively fast. It takes advantage of OpenMP compiler extensions to be multi-threaded. And it's available under an open source license. So how do you use it? This is the very top is a kind of, it's designed to be like a classic Unix command line program. So the simplest case, you say Imfit, you specify a configuration file. The configuration file describes the model you're going to fit to the image. And I'll talk about that in a moment. And then you give it the image to fit. You can add extra command line options. In the second case, you can specify, for instance, a subset of the image to fit using the sort of standard IRAF X to Y range. You can also fit compressed images. You can even fit images that are available via a URL pointing to a FITS file if you want to. I'm not sure how useful that is, but that's something that comes with the CFITS.io library, which is nice. You can also specify mask images, PSF images for convolution. You can specify saving particular kinds of outputs. Okay, I mentioned it's designed to be fairly fast. The fastest available code is probably Galfit. So for comparison, it's typically about 50% faster than Galfit on the same image, the same model, same starting parameters, if you're using it in single thread mode. But as I mentioned, it's written to be multi-threaded. If you have a computer with multiple CPU cores, it can take advantage of them, both in the image computation and in the PSF convolution stage. And so, for instance, if you have a 4-core CPU, then it's about 3 to 4 times faster. These are some sample timings for fitting an 800 by 800 pixel image with an exponential plus a Core-Sersic. So for Galfit, it's about 45 seconds. In single-threaded mode, Imfit's about 30 seconds. But if you turn on multi-threading, which is actually the default, and this is on a 4-core machine, it's about 9 seconds to do the same fit. If you do PSF convolution, then of course everything takes longer because you're doing all of these fast Fourier transforms. So in that case, Galfit is about 2 minutes. Imfit with a single thread is just under 1.5 minutes. In normal multi-threaded mode, it's 30 seconds. Okay, so when you're fitting a model to the image, what are you fitting? In the case of Imfit, everything is organized on the basis of functions and function blocks. So a function is simply a two-dimensional surface brightness function of some kind, exponential, Core-Sersic, and so forth. A function block is simply a set of one or more individual functions, which all have the same location on the image. That is, they all have the same central x and y values in the pixels. You can have multiple functions in a function block, but you can also have multiple function blocks. So, for instance, you could have a function block for each galaxy in the image if you had overlapping galaxies. Or you could have a separate function block for an off-center component, maybe an off-center ring, an off-center bar. So the individual parameters for each function can be restricted to lie within upper and lower bounds. They can be held fixed. They can be allowed to, or they can be unbounded. So this is an example of a configuration file. So sort of a very, very simple case. We're fitting a single Core-Sersic function. So comments are allowed, a little hash mark in front, a sort of standard Python, Perl style syntax. So x0 and y0 specify the position, the position of the central position. Then you have your two initial guess values. Then you have a Core-Sersic function specified with function, name of the function, and then the initial values of the parameters. So if you wanted to do something a bit more complicated, you could add another function block. And in this case, this function block has a different central position, different x0 and y0, and it has two functions, a Core-Sersic and an exponential. And in each, it's the same basic approach, but now I'm also showing you that you can have lower and upper bounds. So those are the second pairs of numbers separated by commas. And if you go down to sort of the n under the Core-Sersic, you can see there's the word fixed, and that just means that this value has to be held constant. So it's designed to be relatively easy to read and write. So the heart of this, in a sense, is the idea of having your individual functions be separate objects which are easy, and it's where it's easy to create new ones. So at the programming level, the individual functions, Core-Sersic, exponential, and so forth, are C++ classes. There's an abstract base class called function object, and then all of the actual functions that you would fit to an image are derived classes. The way they work is the program sends each object the list of the current parameter values, and then what it does is as it moves through the image, building up the model image, it sends the current pixel coordinates. So the program doesn't need to know anything about how the object itself does its calculations. All it needs to know is the object can accept an initial set of parameters, the x and y coordinates, and the object will return some flux value. And those are added up for each pixel. So this makes it easy to write new image functions. You basically need to write two new files, add a couple of lines to a third file, recompile the program, and you're good to go. So there are, of course, a number of functions that come built in, including the sort of like the standards you would expect: two-dimensional Gaussian, Moffat, Core-Sersic and exponential with generalized ellipse shapes. This is where the ellipse can be varied from a perfect ellipse to something that's more boxy or more disky in shape. Some more unusual things include an exponential with a broken profile. So the inner, it's an elliptical function, but it has an inner exponential, and then beyond a certain radius, it has a different exponential slope. It could be steeper to represent a truncation or shallower to represent an anti-truncation. Elliptical rings with Gaussian profiles. The analytic form of a perfectly edge-on exponential disk. Simplistic forms of edge-on rings. The Core-Sersic model for dealing with really massive elliptical galaxies. So let me show you an example of this in action. This is a continuum image from the Haga survey that Sandesh was just telling us about. So it's a narrow band, approximately R band image of a galaxy with a redshift of about 0.03. And we can do a simple fit where we say, okay, we'll fit this with a Core-Sersic function. And that's what you get. And then you look at the residuals and you see, well, there's actually a lot of structure left in the residuals. So for instance, in the center, there's a lot of flux. We're clearly missing something in the center. There's also negative flux outside the center, and you can also see a kind of faint residual ring structure. So the next thing you might try would be a bulged disk decomposition. In this case, we're using an exponential and a Core-Sersic. Now, in this case, what happens is your exponential gets most of the flux, and then your Core-Sersic is actually fitting what's probably a weak bar. And we look at the residual, and so, okay, there isn't that bright spike left over in the center, but you can still see this ring, and you can still see these sort of offset dark zones where the flux is not being matched properly. So it looks like there's a ring. Let's try adding a ring. So exponential on the left, Core-Sersic probably representing a bar in the middle, and a ring with a Gaussian radial profile on the right. And now the residuals are actually a lot cleaner. You no longer have those prominent dark regions in the middle. And you're left over with actually what's possibly interesting is a slightly sort of a suggestion of an m=1 spiral structure. Yeah. Yes. So the Imfit can use masks. The mask is a Fitz file. The inputs are all Fitz files. The mask can be Fitz file. So in this case, yeah, that bright object is assumed. I've assumed it's some sort of foreground star, so it's being masked. Oh, yeah, absolutely. As I said, I would tentatively interpret that as suggesting that the ring isn't really a perfectly closed ring, that it may be a kind of pseudo ring, that it's a very tightly wrapped spiral structure. Okay, something that's a bit unusual is there are also some examples of what I call 3D integration functions. So these are functions where in each pixel, the model flux for that pixel is the result of a line-of-sight integration through a 3D model that has a luminosity-density at each point in 3D space. So there's an axisymmetric disk, which you can have at any inclination. It has a radial exponential profile. And then in the vertical direction, it has this sort of generalized hyperbolic secant function, which van der Kroijt suggested was kind of a good general function to match the vertical profiles of disks. There's a variant of that which has the radial profile be a broken exponential, which might be useful for truncated disks. And there's also an example of a Gaussian ring, which can be elliptical rather than axisymmetric. In the bottom here, I'm showing you the axisymmetric disk 3D model seen at three different inclinations. So on the left is 75 degrees, and we go to 85 degrees and then 89 degrees, almost but not perfectly edge-on. And in fact, that diamond-shaped is what you get for the perfectly analytic edge-on model. The advantage of this model is, however, of course, you can vary it all the way to face-on. So here's an example of using these 3D integration models. This is a Spitzer 3.6 micron image of an edge-on spiral, IC 5176. You can see that there's very little, there's clearly a thin disk, as it turns out if you look carefully at the isophotons, there's evidence for a thick disk as well. So we'll fit that with 2 3D disk models. One, the best fit, this is what we'll call the thin disk model. And there's another component which approximates the thick disk. So the combined model with a small central component, which is modeled as a Core-Sersic, it may in fact be something more like a nuclear star cluster, looks like that. The residuals look like that. So most of the galaxy is pretty well modeled. You can clearly see residuals aligned with the central disk. Those are, in this case, what we're probably seeing are some combination of spiral structure, star formation, and very, very strong dust lanes that are still affecting the 3.6 micron. But this lets us, for example, look at the different luminosity contributions for the different components. So this central little Core-Sersic component is not even 2% of the total light. The thin disk accounts for about 72% of the light. It has a scale height of about 260 parsecs. The thick disk is about 27% of the light, and it has a scale height of about 1.5 kiloparsecs. Now, in fact, I left the vertical component, the generalized vertical component free. In both cases, they converged towards approximately an exponential profile. So you have a thick to thin disk scale height ratio of almost 6. You have a thick to thin luminosity ratio of about 0.37, which, if you look at the Comeron et al. 2011 study of edge-on galaxies, for a galaxy with the same rotation velocity as this guy, that's actually right in the middle of their distribution. I do. I don't have them with me. But now, I should point out that this is Spitzer 3.6 micron. So the seeing is, close to 2 arc seconds. The reality is you probably can't really pin down the precise nature of the scale height very accurately with resolution this low. The other thing I want to point out is that in this case, the best fitting thin disk is not perfectly edge-on. It has an inclination of about 87 degrees. Again, this is something that you would really want much higher resolution to be able to pin down properly. It does suggest to me, as a kind of aside for people who like to study edge-on galaxies, that the question of what is the vertical structure of a disk is maybe some combination of, people don't always worry about what happens if your disk is at, say, 88 or 89 degrees. Your line of sight, what you see on the sky is an integration through that. And so in that case, something that might have an exponential profile intrinsically would give you something more like a secant h squared if the inclination is perfectly edge-on. Something to sort of an aside. Okay, so let me finally note that there are 3 different minimization algorithms, and I'll talk a little bit about what you're minimizing. Levenberg-Marquardt least squares. This is very fast. It's robust. It has a disadvantage that it can sometimes get caught in local minima in the fit landscape. There is also a simplex minimizer, which is less sensitive to local minima, and which is also slower. If you really have time to waste, there is a genetic algorithms minimizer called differential evolution. In principle, even less likely to get trapped in local minima, and it's even slower, of order 50 to 100 times slower. So some things that this is already being used for. Our group at MPIE has been using this for the decomposition of images as part of measuring supermassive black holes. We're doing this for both S0 and spiral galaxies. It's been used to fit components of a galaxy that have been initially decomposed using stellar kinematics. It's also been adapted for some preliminary testing of the Euclid photometric pipeline. And in fact, André Luiz de Amorim in Brazil has written some preliminary Python bindings so that you can actually run this from within Python directly. Okay, so in the last 5 minutes, I'm going to talk a little bit about an issue that comes out of this, which is what are you minimizing when you minimize some statistical value to fit an image? So the idea is that you've got a model which produces a set of fluxes, in this case fluxes in each pixel, and you're comparing it to an image, and you want to match the model to the image. And this means minimizing some sort of overall parameter. Okay. Most astronomical images typically have two noise regimes, two sources of noise. One is Poisson Statistics. Those are your classic detected photoelectrons. And the other is some sort of Gaussian noise contribution from sources such as read noise, although you don't always have this. For instance, if you have an X-ray detector, those often have essentially no noise. Now, one way to think about how you do the fitting is a maximum likelihood approach. The idea is that you want to maximize the total likelihood of a model. You do that by maximizing the product of the individual pixel probabilities, and that's the probability of the observed data given the current model value. So you multiply them all together. It's actually almost always simpler to take the logarithm of that, take the negative of the logarithm, and then minimize that value. So you would think that, okay, minimizing the log likelihood of some model which combines Gaussian and Poisson contributions shouldn't be too difficult. I mean, the Gaussian is really simple. We know how that works. Poisson is actually really simple, too. Unfortunately, it actually looks like this. And I stick this up here basically just to scare you. This is the minus log likelihood of the proper combination of Poisson and Gaussian statistics. It's for each pixel, you have to compute the infinite sum, the product of two exponential functions, and a factorial. So my reaction when I kind of tracked this down and saw the proper expression was essentially this. Let's not go there. So there are two simple solutions. The one that almost everyone uses is this. You basically say, okay, let's pretend the Poisson contribution is really a Gaussian. And we'll use the approximation where the sigma of the Gaussian is equal to the square root of the flux level you're talking about. And in that case, this negative log likelihood becomes the classic chi-squared. You minimize the chi-squared. There are actually, at one point, there are three ways of figuring out what sigma is. You can take it from the data values. This is probably the most common thing to do. Or you can take it from the model values. That is, take the square root of the model flux. Or, of course, if your reduction pipeline gives you some sort of error or variance map that you think accurately reflects the noise contributions, you can use that. There's another possibility, which is to ignore any possible Gaussian contributions and use actual Poisson statistics. In other words, the probability is that expression on the upper right. If you take the minus log likelihood of this, then you get what's called the Cash statistic from Cash 1979. And as you can see, this is actually a really simple expression. It's as simple as the chi-squared expression. And among other things, if you're dealing with a low-count regime where you know the Gaussian approximation to Poisson statistics isn't really very valid, this is the ideal thing to use. Now, should you use one or should you use the other? So what I'm going to show you are some results of testing different approaches with model images plus a handful of real galaxy images. So this is basically, in each case, I'm generating 500 artificial images, let's call them that. This is a simple elliptical n equals 3 Core-Sersic model. I do this in three different signal-to-noise regimes. One where the background level is about 20 electrons per pixel. And then two other regimes which are essentially 5 and 25 times the same. It's basically like having a 5 or 25 times longer exposure time. The images are generated using proper Poisson statistics, optionally with Gaussian read noise added on afterwards. And they're fit using Imfit, using the database chi-squared, the model-based chi-squared, and the Cash statistic approach. So what do you get? What I'm showing you here are the distribution of models from fitting the 500 different artificial galaxy images. The left-hand panel is the Core-Sersic n value, and the vertical dotted line shows you the true value, which is 3. The middle panel shows you the half-light radius in pixels. Again, the vertical line is the dashed vertical line is the true value. And the right-hand panel shows you the surface brightness at the half-light radius. And what you can see is that when you use the standard data-based chi-squared approach, there are systematic biases. You underestimate the Core-Sersic n by about 10%, and the same thing for the half-light radius. Okay, what if we use the model values to do the chi-squared minimization? That looks like this. You get a different bias. You get a bias that's about half as large in the opposite direction. What if you use the cache statistic approach? You get this. The cache statistic approach is basically unbiased. Now, this is for the relatively low signal-to-noise regime. If we go 5 times higher, it looks like this. So now you can see that the cache statistic is still unbiased. The chi-squared statistics, the bias is still present, although it has shrunk significantly. I'm sorry, what I skipped over, let me go back here. The dashed histograms are what you get if you take the images and you add some Gaussian read noise, that say sigma equals 5 electrons. So in this case, the cache statistic is no longer, strictly speaking, correct, because there is Gaussian noise in the image. What the Gaussian noise does is it decreases the bias slightly, but the bias is still present. Okay, medium signal-to-noise regime, bias shrinks. The difference between the Gaussian and non-Gaussian noise is essentially gone. So chi-squared fits yield biased model parameters. Fitting with the model-based chi-squared gives you a smaller bias, and the cache statistic fits are essentially unbiased. This is spelled out rather nicely in the case of fitting X-ray data by Humphrey et al. 2009. And if you want to know more about the details of this, I would actually suggest you look at that paper. So last point, does this apply to real galaxies? Is there any evidence that this works for real galaxy images? Okay, what I'm showing you on the left is a kind of condensed summary of the previous slide. This shows you the relative bias of the chi-squared fits as a function of the background sky level, sort of the signal-to-noise level. So in the upper panel, these are the results from doing the database fits. The red is the half-light radius measurement. The green, the below is n, Core-Sersic n, RE, the half-light radius. So as you go towards higher values of the as you have a higher background level, the bias shrinks. The little wiggly line around 0 is the cache statistic results. Okay. So what I'm going to show you are the results of fitting 3 elliptical galaxy images. A set of 3 images from Sloan, the U, G, and R images of a single galaxy, and also for 2 other galaxies, short and long exposures of the same galaxy in a single band. I can't show you what the bias is relative to the true value because I don't know the true value for these galaxies. So what I'm going to show you instead is the bias of the chi-squared fits relative to the cache statistic fits. And of course, in the model galaxies, the cache statistic fits has 0 bias relative to the true value. So it's sort of an equivalent plot. And it looks like this. The main thing to realize is that the pattern of the biases of the chi-squared fits relative to the cache statistic fits are exactly the same. The absolute levels are not. But the fact that N and RE are biased low when you're using data-based chi-squared, and they're biased high when you're using model-based chi-squared. And in fact, the bias is about half in the model-based case as it is in the data-based case, which is exactly what we saw for the artificial galaxy images. So there is some evidence that chi-squared fits to elliptical galaxies using a single Core-Sersic component will give you the same pattern of deviations. So, great, you should always use a cache statistic fit when doing fitting images of galaxies. Well, in principle, yes, lower bias, even when there's read noise. Probably really important, I would suggest whenever your background level is, say, less than about 100 electrons per pixel. Now, the drawback is that the cache statistic is usually a number less than 0. This doesn't matter, except that the Levenberg-Marquardt algorithm, which is really, really fast, is a least squares minimization. It assumes what you're minimizing is 0 or positive. So you actually cannot use it. You have to use a different minimization algorithm. With Imfit, you can use the simplex algorithm, but that is about 5 or 10 times slower. There's also, if you believe your external error maps from some data reduction pipeline, then you're kind of basically saying, okay, you have to use chi-squared if you want to use those. If you're going to use chi-squared, I would point out that the model-based chi-squared that is estimating your individual pixel errors from the model values has about half the bias of the data-based chi-squared. Okay. So to summarize, I've talked about Imfit, fast, flexible, extensible image fitting code for decomposing galaxies. It's meant to be easy to add new components. There are multiple minimization options and algorithms. And if you're fitting galaxies, be aware that fitting using standard chi-squared approaches can lead to minor biases in your fitted parameters. If you fit using the cache statistic approach instead, you apparently do not get these biases. And I will leave you with the URL of the source code. Compiled versions for Mac OS X and Linux are available. The source code's available, documentation, sample files. Download it and play with it. Thank you.
So, another few minutes for a couple of questions.
Peter, I understand that you have it, but you didn't mention, so what about the sky? So you also leave the sky free for fitting?
Well, you can. There's an option to have essentially a flat background as a separate image, as a separate function. My personal feeling is essentially the same as that of Chen Peng's, is that you should probably not have that be a free component in your fit. For instance, if you're fitting an elliptical galaxy with a Core-Sersic component, you're basically saying, okay, and you're letting the background level be a free component of your model. You're basically saying, I assume the galaxy is perfectly represented by a Core-Sersic component at large radii. And so the background level will be adjusted to make sure that that works. My personal feeling is that you should subtract off the background as a previous stage without assuming something about what the model of the galaxy itself is.
For massive survey classification, is there any way to integrate Imfit with things like Sextractor?
I don't personally have anything that does it, but it shouldn't be too hard. I mean, people have integrated things like GIM2D and GalFit into those sorts of things. It basically, the input needs to be a FITS file, the masks can be FITS files, the configuration file that describes the model is a simple text file similar to what GalFit uses. So there shouldn't be anything stopping you from doing that.
How are the degeneracies handled, and how do you get your uncertainties?
Okay, so the uncertainties I can answer. There are two ways to get uncertainties. If you're fitting using the Levenberg-Marquardt method, then that automatically produces a set of uncertainties. This is based on assuming that the chi-squared landscape in the vicinity of your minimum is parabolic shaped, and you do something to the Hessian matrix, and you get a set of symmetric error estimates. Now, you don't get this if you're using, say, the simplex minimization or the differential evolution. So there's a different option, which is that after you finish the fit, you can have it do Bootstrap Resampling. And so what it will do is it will take your image, it will generate a new data image via Bootstrap Resampling from the original, and rerun the fit. And you can tell it to do that however many 100 or 1,000 times you want. And then what you will get at the end of that, which unfortunately takes a while, is a set of asymmetric error estimates. Rather than, so in some cases, depending on the nature of the parameters of your function, your error estimate will be, the plus or minus values really are different, and they're not just symmetric. So those are the two options that you have.
I just have a question. How much does it affect that you have, for example, the correct inclination? You showed this example where this really, really inclined galaxy, but also I can imagine if you have some galaxies with more complex structure with bars and so on, where it's quite difficult to get the right inclination, and then you say you can add some more components, but how reliable will this be in the end?
I don't actually know yet. I haven't done a whole lot of testing with sort of complex, highly inclined galaxies. But that may indeed be a problem. And of course, you can specify that the inclination should be fixed to a particular value or should lie within some narrow range if you're worried about that.
Okay, so yeah, let's thank our speaker once more, and then you're welcome to join for the coffee and ask more questions.